Welcome to 22nd lecture on complex variables and transforms. In our last lecture CVT-21 we started studying inverse Laplace transform, and we'll continue that even in this lecture. Here's a small recap. F of s, the Laplace transform of a signal f of t, is written as Laplace transform of f of t. Applying Laplace inverse on both sides yields f of t is inverse Laplace of f of s. And we studied partial fraction too, when we cannot apply the linearity property directly. We studied that we apply partial fraction first and then we apply the linearity property to compute the inverse Laplace transform. We studied that in our last lecture CVT-21, available on my YouTube channel. Right, in this lecture we'll solve an example where f of s is equal to 3s over s minus 1 times s squared plus 4. Before we apply the linearity property to solve inverse Laplace transform for f of s, we must have to apply partial fraction to segregate these two terms, s minus 1 and s squared plus 4. Right, we write it as a over s minus 1, and the second term s squared plus 4. For that we have to write bs plus c in the numerator instead of only b, because we have a squared term here. If you have a squared term here, we have to write bs plus c, a constant, times s plus another constant. We cannot just write b, right? So why did we write a here? Because we have s to the 1 here, therefore we write a over s minus 1. But here we have second power of s squared, therefore we have to write bs plus c. And then we take the LCM, s minus 1 s squared plus 4, multiply this here, s minus 1 is multiplied with this numerator, and we solve unless we reach here, and we see that and there is another interesting observation that the two fractions are equal and their denominators are also equal, therefore their numerators have to be equal. So we have put them equal, and now we are able to compare coefficients. First we compare coefficients of s squared. A plus b is the coefficient of s squared on the right hand side, but on the left hand side we have 0. So a plus b is equal to 0. This is equation number 1. For s we have c minus b on the right hand side, and 3 is the coefficient of s on the left hand side. So therefore c minus b is 3, and for constants is 4a minus c on the right hand side, but on the left hand side we have 0. 4a minus c is 0. That's all. From here we reach here. What we have done is that we have computed b to be equal to, or b to be equal to minus a. b is minus a. From this equation number 1, we have b is equal to minus a. We put b is equal to minus a here, so it becomes c minus into minus a, or c plus a. So c plus a becomes 3. This is what we have written here, c plus a is equal to 3. And from equation number 3 we have 4a minus c, or minus c plus 4a is equal to 0. So if we add these two equations, this cancels, and 5a comes out to be equal to 3, or a is 3 over 5. Now we can put this a is equal to 3 over 5 here. b is minus a. So if a is 3 over 5, b is minus 3 over 5. Once we have computed a and b, we can put them in an equation like here. C is b plus 3 in equation number 2. If you put this b in equation number 2, c is taking b on the other side, becomes b plus 3. So c is b plus 3. Solving this gives 12 over 5. So now we have computed a, b and c using these three equations, 1, 2 and 3. So it's very simple. So now we have a, b and c available, and we are ready to plug these here. Before we plug these items, we can verify that the a, b and c that we have just computed are really correct, right? So what we are going to do is we have to implement it to put these here. 3 by 5, a is 3 by 5, we put it here, b we put it here, and we put c here. So a is 3 by 5, b is minus 3 by 5, c is 12 by 5. So put everything we have computed, a, b and c. We plug these values here and we see we keep on solving unless we reach here 3s over s minus 1 times s squared plus 4, the left hand side. So we have proved right hand side to be equal to left hand side, and actually we have verified that the values of a, b and c we have just computed, they are really true. Right, so now we'll take this equation and we'll apply the inverse Laplace transform. Let's apply inverse Laplace transform here. The inverse Laplace of this would be the inverse, applying linearity property, the inverse Laplace of this plus the inverse Laplace of this. So inverse Laplace of 3 over 5 can be taken out, 1 over s minus 1. Laplace inverse of 1 minus s over 1 is e to the t. This is e to the 3 over 5 e to the t. The first term gets right. The second term can be further divided as minus 3 over 5s over s squared plus 4 plus 12 over 5 over s squared plus 4. So they can be segregated because a plus b over c. If we have a plus b over c, we can write it as a over c plus b over c. So it's a over c plus b over c. When we write a over c minus 3 over 5 can be taken outside, s over s squared plus 4, this is, this is inverse cosine of 2t, inverse cosine of omega, where omega is 2 here. And the last term is 12 over 5 over s squared plus 4. 12 over 5 can be written outside. 1 over s squared plus 4, if we introduce a 2 here, we multiply it with 2 and we divide by 2, it becomes 12 by 10 and sine 2t, because 2 over s squared plus 2 over s squared plus 2 squared is the inverse Laplace is sine 2t, sine omega t, where omega is 2. So this is how we can, and of course we have to multiply all this with u of t, because the function, the time domain function, it is valid only for values of t greater than or equal to 0. Right, that's all for this lecture. Thank you.